Picture this. It is 3 a.m. in Dubai. The year is 2007. 630 meters. Above the desert floor, an engineer named Ahmad Al-Marzuki is staring at a pressure gauge, and the number it's showing him is wrong. The concrete pump is failing. The mix is segregating under its own weight before it even reaches the formwork. And at that exact moment, the entire upper section of what will become the world's tallest building, the Burj Khalifa, is at risk of structural compromise. Here's what the brochures don't tell you. The Burj Khalifa's concrete was chilled to 15 degrees Celsius before pumping, because at that height, desert heat would cause it to set prematurely inside the delivery pipe. The project's engineers, led by the Chicago-based firm Skidmore, Owings and Merrill, had to invent a new concrete pumping protocol on the fly, because no one had ever pumped concrete to 600 meters before. No one. That moment, 3 in the morning, a failing pump, and 600 meters of concrete mix hanging in the air. That is where this story really begins. Not with ambition, but with the terrifying, beautiful physics of building against gravity. 10,000 years ago, before the wheel, before written language, a group of humans did something that defied every survival instinct they had. They started stacking stones upward, not for shelter, not for warmth. For a reason archaeologists still debate today. The Tower of Jericho, located in the Jordan Valley in what is now the West Bank, stood just 8.5 meters tall. That sounds laughably modest. But consider the context. These people had no metal tools, no draft animals, no mechanical advantage whatsoever. They were moving multi-ton limestone blocks using human muscles, wooden levers, and, we believe, a system of earthen ramps that were then dismantled. Archaeologist Kathleen Kenyon, who excavated Jericho in the 1950s, concluded this tower was not defensive. It was symbolic. It was the first time a human civilization said, "We are here. We reach upward. We are not just animals on the ground." The Great Pyramid of Giza, built around 2560 BC, took that instinct and scaled it to the divine. At 146.5 meters, it held the record as the tallest man-made structure for approximately 3,800 years. Let that number sit with you. 3,800 years. No civilization on Earth could match it. And the engineering behind it was not primitive. It was forensically precise. The base of the Great Pyramid deviates from perfect level by less than 2.1 centimeters across its entire 230-meter footprint. Modern laser-guided survey equipment would struggle to match that accuracy. For decades, historians assumed the pyramids were built by slaves. The archaeological record tells a different story. Excavations near Giza have uncovered workers' villages with hospitals, bakeries, and organized administrative records, evidence of a paid, skilled, rotating workforce. These were not chains and whips. This was the ancient, world's most sophisticated construction management operation. But here's the physics that every civilization after Egypt had to confront. The higher you build, the more catastrophically your own structure works against you. Engineers call it compressive load. When you double the height of a building, you don't double the load on the base. You square it. Every meter of height adds not just material weight above, but forces multiplication below. This is why for millennia, the tallest structures in the world were wide, not tall. Pyramids, ziggurat temples, earthen mounds. Height required mass, and mass required width. That was the fundamental equation of pre-industrial architecture. The Middle Ages broke that equation, partially. European cathedral builders discovered the flying buttress, an external arched support that transferred the lateral forces of a tall stone wall outward and downward. It was a revolutionary insight. Suddenly, stone walls could be thinner, taller, pierced with vast stained glass windows. The flying buttress was the medieval equivalent of carbon fiber. The Lincoln Cathedral in England, completed in 1311, used this principle to reach approximately 60 meters, surpassing the Great Pyramid for the first time in recorded history. But medieval builders learned a brutal lesson that ancient Egyptians never had to face at those heights: wind load. Here is what wind does to a tall structure. At ground level, wind exerts roughly 15 kilograms of force per square meter in a moderate gale. At 150 meters, the height of those Gothic spires, the same storm exerts force at nearly 2.5 times that magnitude, and it isn't steady. It pulses. It resonates. If the resonant frequency of the wind matches the natural frequency of the structure, it amplifies, a phenomenon called vortex-induced vibration. Several medieval cathedral spires didn't slowly deteriorate. They resonated themselves apart in storms and collapsed. Stone, it turned out, handled compression well, but had almost no tensile strength. It could not flex. It could only break. That single material limitation put a ceiling on human ambition for almost 5 centuries. In 1856, Henry Bessemer's converter process made mass-produced steel commercially viable for the first time. And within 3 decades, it had completely rewritten the rules of construction. Steel had something stone never could: tensile strength. It could be pulled, bent, flexed. A steel-framed building could sway in the wind and survive. In fact, it had to sway. A building that refuses to flex under load doesn't stand. It shatters. The Eiffel Tower, completed in 1889, was not just a monument. It was a live engineering experiment. At 300 meters, Gustave Eiffel himself calculated that the tower's tip would move up to 12 centimeters on a hot day due to thermal expansion on the sun-facing side. He designed it. He published his calculations. The Eiffel Tower was the first major structure where the engineering math was made completely transparent to the public, and it terrified people. Not because it was unsafe, but because the math proved it was alive. Then came New York, and with it, something new. The skyscraper wasn't born from kings or gods. It was born from economics. By 1900, Manhattan land values had risen so dramatically that the only logical direction for development was vertical. The Empire State Building, completed in 1931 in the depth of the Great Depression, rose at a pace that still shocks construction. Engineers today average of 4.5 floors per week. Roughly 3,400 workers were on site daily, many of them Mohawk ironworkers, from the Kahnawake Reserve in Quebec, known for their extraordinary fearlessness at heights, alongside European immigrants and Depression-era laborers working for as little as $50 a week. The famous photographs of workers eating lunch on unguarded steel beams 400 meters up were not staged. Workplace safety standards in 1930 were, by today's standards, essentially non-existent. Official records list 5 construction fatalities. Historians believe the real number was significantly higher. Now back to Dubai and the pump at 3 a.m. The Burj Khalifa's chief structural engineer, William F. Baker of Essom, solved the wind problem with a concept he called the buttressed core, the building's I-shaped footprint, visible clearly from above, is not aesthetic. It is aerodynamic. As wind hits one face of the Y, it's redirected around the building's geometry, breaking up the coherent vortex that would otherwise form. The structure essentially confuses the wind. It never lets it develop a single dominant force vector. At 828 meters, the Burj Khalifa also confronts a problem that sounds almost surreal: the Earth's curvature. The building is tall enough that the base and the top are measurably different distances from the Earth's center of gravity. The tidal forces at the top, the slight gravitational pull of the moon, are technically different from those at the base. These are unmeasurably small in practice, but they exist. The Burj Khalifa is, in a genuine physical sense, in 2 different gravitational environments simultaneously. The elevator system required equally radical engineering. Standard elevator cables become unusably heavy beyond about 500 meters. The Burj Khalifa uses Cone's ultra-rope system, a carbon fiber composite cable so light that the cable itself contributes almost no load penalty at height. The elevators travel at 10 meters per second. Without pressure equalization in the elevator cabins, passengers' eardrums would rupture from the rapid altitude change. The cabins are pressurized like aircraft. Cost, approximately $1.5 billion US. Workforce, over 12,000 migrant laborers at peak construction, drawn primarily from South Asia. Human rights, watch and multiple labor advocacy organizations, documented conditions, including passport confiscation, wage theft, and overcrowded labor camps. The Burj Khalifa is a monument to engineering, genius, and to a labor system that many consider a modern ethical catastrophe. Both things are true. Dark Chapter does not look away from either. Here's your Dark Chapter dilemma for today. The Burj Khalifa required tens of thousands of migrant workers, many in documented exploitative conditions, to build a structure that now defines a city's identity and generates billions in tourism revenue. So here's the question. Should a civilization's greatest architectural achievements carry a permanent record of the human cost it took to build them? Drop your answer in the comments. We read everyone. Once the Burj Khalifa existed, the engineering conversation shifted. The question was no longer, can we build a kilometer tall? The question became, what is the actual physical ceiling? Japan's Shimizu mega pyramid concept proposed a 2-kilometer tall structure over Tokyo Bay, housing approximately 1 million people. The concept was born from genuine urban pressure. Greater Tokyo's metropolitan population exceeds 37 million people, making it the most densely inhabited urban zone on Earth. The mega pyramid wasn't fantasy. It was a pressure release valve, a serious proposal to absorb population growth in a country with almost no available flatland. The material problem was the same one that has constrained every megastructure since Jericho. Conventional steel and concrete would collapse under their own weight at that scale. The mega pyramid's feasibility study specifically identified carbon nanotubes as the enabling material. Carbon nanotubes have a theoretical tensile strength approximately 100 times that of high-grade steel at 1/6 the density. The problem is not the science. The problem is manufacturing. As of today, the longest continuous carbon nanotube fiber ever, produced in a laboratory setting measures less than half a meter. A 2-kilometer structure would require kilometers of the material in flawless, defect-free condition. We are not there. We may be decades from being there. The Exceed 4000 concept, a 4-kilometer structure proposed by the Taisei Corporation, pushed the parameters even further. At 4,000 meters, you exit the atmospheric boundary layer. Wind behavior becomes stratospheric. Temperature differentials between base and apex exceed 25 degrees Celsius. The structure would require internal climate control systems for each of its proposed 800 floors. It would need an independent water supply system, waste processing, emergency services, in effect, an entire city's infrastructure duplicated inside a single object. The evacuation problem alone may be unsolvable. If a fire breaks out on floor 400, conventional evacuation models suggest it could take over 8 hours to clear the upper sections. Beyond the atmosphere, the concept shifts entirely. You're no longer building against gravity. You're building with it. The space elevator, first proposed theoretically by Russian engineer Konstantin Tsiolkovsky in 1895, and later formalized by Arthur C. Clarke in his 1979 novel, The Fountains of Paradise, operates on a counterintuitive principle, a cable anchored to Earth's equator and extending to geostationaries. Orbit at 35,186 kilometers would not fall. The section of cable above geostationary orbit would be pulled outward by centrifugal force, the Earth's rotation, while the section below would be pulled inward by gravity. The two forces balance. The cable achieves static tension. Climber vehicles, essentially motorized clamps, would then ascend this cable, delivering payload to orbit for a fraction of rocket launch costs. Current estimates suggest a space elevator could reduce the cost of placing 1 kilogram of payload in orbit from approximately $20,000. SpaceX Falcon 9 pricing to somewhere between 100 and 500. That's not an incremental improvement. That's a civilizational shift. The material requirement is brutal. The cable would need a specific tensile strength, the strength-to-weight ratio of at least 49.5 megapascals per kilogram per cubic meter. The strongest steel cable achieves roughly 4.x. Kevlar achieves around 3.6. Carbon nanotubes, theoretically, achieve over 46. Theoretically. No. One has manufactured a cable length quantity, and a space elevator cable would need to be thousands of kilometers long without a single critical defect. Because a break at orbital height doesn't just damage the cable, it creates a kinetic debris event that could potentially strip low Earth orbit of usable space for a generation. Every generation has stood in front of the previous generation's greatest structure and said, that is the limit. Every generation has been wrong. The Tower of Jericho was the limit. Then the Great Pyramid stood for 3,800 years. Then Gothic spires. Then steel towers. Then the Burj Khalifa. What's changed isn't human ambition. What changes is material science. Every revolution in height has been preceded by a revolution in materials. Stone enabled pyramids. The flying buttress enabled cathedrals. Steel enabled skyscrapers. Carbon fiber enabled supertel elevators. Carbon nanotubes, if we ever master their production, will enable something that today we would call impossible. But here's the darker truth that the history of tall structures reveals. Every mega structure in human history has been built by the powerful, for the powerful, and constructed by the vulnerable. The Great Pyramid by organized labor we're still debating. The cathedrals by medieval serfs. The Empire State by Depression-era migrants earning poverty wages. The Burj Khalifa by workers whose passports were sometimes taken at the airport. The physics of height improves with technology. The ethics of how we build, that has been remarkably consistent. Every civilization tells you what it values most by what it builds tallest. The pyramids whispered, "We are close to the gods." The cathedrals declared, "Our faith outreaches all others." The early American skyscrapers announced, "Our economy is the most powerful force on earth." The Burj Khalifa said, "We are the future, and we are open for business." What will the next structure say? A 4-kilometer vertical city housing 1 million people might say, "We solved the urban crisis." A space elevator anchored to the equator might say, "We left the cradle." Or, if we don't solve the labor ethics, the environmental cost, and the human displacement, it might say exactly what every structure before it has said: power builds upward, consequences fall downward. The question was never really how high humans can build. The question was always, what are we willing to do, and who are we willing to sacrifice to get there? That's your dark chapter for today. Here's the final dilemma. If a space elevator were built tomorrow, and it reduced the cost of leaving Earth to almost nothing, should access to it be a human right, equally available to all nations? Or would it, like every great structure in history, become a tool of the powerful? Comment below, because this isn't a hypothetical. This decision is closer than you think. Like this video if it made you think differently. Subscribe to Dark Chapter, because the most important stories aren't the ones history celebrates. They're the ones it quietly buries.